Okay, welcome once again to yet another problem solving session with our special maths. So this problem corner for February, and this is the last bit, the bonus um, problem for the geometry section. So here we go. So find all pairs of circles in level 1. So the initial circles I colored in blue. So find all those the circles, pairs of circles, so that the radical axis and radial axis of those pairs are now the radial and the radical axis of another pair. So kind of switching between radial and radical axis. So I'll just explain a bit about radical axis as well as radial axis. So so for radial axis is more straightforward. So you have two circles, you have their centers, then there is a unique line passing through the centers. So it's just as simple as this. So this is radial. Okay. Then radical axis is a line that is perpendicular to this line. Okay. But basically, it's a line that is a collection of points such that the power of the point to both of these circles is the same. So basically, if you draw any line from P cutting across the two circles, let's say at X, Y, Z, W, then the power of point P for this first circle will just be Px minus Py. The power for the respect to the other circle will be Pz and Pw. So those points are satisfied equality for these two figures. Those are the points that lie on the radical axis. So it turns out they lie on a straight line. That line is perpendicular to the radial axis. So particularly if circles touch, it becomes much easier to figure out what the radical axis is. So that becomes the line passing through their points of intersection. And the simple reason is that for the point of intersection, P here, that's if you draw any line from P to the first circle, for instance, it will meet at 2 points. The first will be P itself and another point. So here in this case, it's like X is equal to P. And so the power of the point there is going to be 0 because the distance between P and X is just the same point, so that's 0. So, and since P also lies on the other circle, the same happens. So just get 0 equals 0. So it lies on the radical axis. And the same applies to the second point of intersection. And then drawing that line creates the radical axis. But if they don't touch, it's not so straightforward. So you may need to consider other things. But one thing you can consider tangent line from, let's say this is P now, tangent line from P to the circles. So yeah. So when it's tangent, it means it touches the circle at generally the line should cross the circle at 2 points. At the tangent part is as like taking the 2 points to end up being the same point, right? So in this case, this point here will serve as both X and Y. So the power of the points there will be just a Px squared, since X and Y are the same. So on the other hand, you have here, if this is W, then it's T also Z and W. The line P, W only touches it once. So that will serve as both points. And then you get the power to be the product, which is just PW squared. So since P lies on the radical axis, these two expressions must be the same. And so Px must be equal to Pw. So in fact, if you do the same for other tangents, like this one, they all have the same length. So in fact, you could draw a circle centered at P, crossing the two circles at those tangent points. Tangency points. Okay, so that's just a basic introduction to this. So you could just look it up to get more ideas. So Let's move now to GeoGebra and see what we could do. Okay, so you're going to try to use a bit of symmetry to understand how to go about this. So if we take for example, let's say, okay, these up here. Okay, so let's say we take for example circle A. Look at circle A, D, E, H. Okay, so once you have this circle, there's exactly one circle that that basically doesn't intersect this circle at any of the original points. So that's because apart from these 4 circles, these 4 points, there are only 4 other points. So if you're going to have another circle that has nothing to do with this point, then they have to be created from B, C, F, and G. So in this case, we have this circle and this circle. Here they didn't touch, but they might cross, or even if they cross, they wouldn't cross. They'll cross at points like this that we don't really know much about. So they kind of go in pairs like that. So this could be considered like the complement of this. Okay. And those are the pairs we are going to show that they are going to be we are going to consider radical and the radial axis of this. So for instance, let me zoom out for a bit. So for instance, you have for these 2 specific circles, you have the center of AD HE at S, and the other center is at K. Okay, so the radial axis is just simply a line joining SK. Now, as for the radical axis, we just know it's going to be between these 2 circles. We're not so sure. Is that for this one, perhaps you could find another circle where this now is the radial axis of that circle. So meaning this has to pass through the center of those circles. In the diagram, you might be suspecting these guys probably, or maybe this guy is somehow involved. I'm not so sure, but yeah, that's just a sketch anyway. So so maybe something like that. And then for the 2 circles whose centers are now on that radical axis, their own radical axis will now coincide with this as well. So one result. Well, there's some kind of balance and symmetry going on. So when you have A, D, E, H, and B, C, F, G. So when you have those two setups, so let me erase some of this. So I'm just going to consider, let me draw a more accurate line first. So this radial axis of on one end. Okay. So we want the radical axis for these 2 circles that I highlighted. So let me highlight them a bit more. Okay, let's see. Okay, let me just do this to highlight them a bit more. Okay, so we're looking at these 2 circles. Yeah, all right. And we want their radical axis. So I'm going to show you what is actually going to be. Then we're going to just prove it. So you could do some exploring. So it's going to be this guy. and I'll also highlight the respective circles. Yeah. And this one. So this what we have. So we're going to show this. Okay. Change the color of this a bit. Go with this. Okay, so let's just go with this. All right. So I'm going to show that these two pairs of circles like have the required. Okay, I think I got one of this wrong. This is the wrong one. Sorry about that. Okay, so let's do this again. Okay, the one I actually wanted was one centered at R, so that's this one here. Go with this. Okay, yeah. Okay, so let me identify that and then work from there. So the other pair to this, so try to figure things out. So that pair will be A, B, E, F, and also the other ones, so that's C, D, G, H. Okay, so if you observe well, you see that we have some things in common here, which is AE, and we also have some stuff here in common, which is CG. On the other hand, if we swap them, we also get common parts, BF and TH. So as a matter of fact, this is just placing this, should I say, these segments together. So these ones, they are purple, and these other ones here are green. Remember, if we have two purple and two green, generally, those are what forms like the circles we're dealing with. So if we take any combination of this, you see that they will form some circle. So once we have any setting like this, yeah, and we find a corresponding circle. So let's say we start with how to go about it. We start with AE, then what we're left with for the purple will be CG. And then for AE, you see that we have some circles passing through A and E. Right? So now for those circles passing through A and E, so circles passing through A and E, you see that it also passes through B and F, and then there's another one passing through D and H. So if you pick any of them, the other one will follow automatically since you don't have any 5 points on a particular circle. And that will create your complete diagram for the pairs we need. So if you take this pair and this pair, so they are going to form the first pair of circles we're looking at, and then we cross it the other way, and then we get the other pair. All right, so what to now show that we actually have, for such an instance, we actually have that the radical axis of one is the radial of the other. So if you observe, you also see that the point Z is actually on both lines. So, and Z, if you remember, Z was actually Z, A1, and W. We actually, the honorable mentions for the previous level, we are looking at where all those green and purple circles met. So we had 3 particular points that form like a partitioning of those circles. So it was not the best because we also had U and V, but they also work. So this is where we'll get to see more about those particular points. Okay, so I'm going to now take this. I'm just going to take this in a, let's see. Okay, let's make use of this place here. Okay, so wherever these two lines meet, so what are these lines? So we're going to define them using their radial definitions. So we know the orange ones are the centers of certain circles. So just join these two pairs of centers according to the figure here. Wherever they meet, that is Z. Just call it Z for now. Okay, so we want to show that both of these lines are now radical axis of the opposite pair of circles. Okay, so let's just focus on one pair of circles and get that done with. So we look at this circle and this circle. We want to show now that Rn is radical axis of those two circles. Okay, so we have to involve the centers. So what we're going to do is, remember for radical axis, if we have any 2 points on radical axis, we just need the power of those points with respect to those circles to be equal. Okay, so that's just what we need. So here, particularly, if you observe R being the center of DHCG, so we have DH there, and S also being the center of DHAE, so we still have DH in common. So the perpendicular bisector passes through both S and R, right? So perpendicular bisector of DH. So if you look at this, this was supposed to be a circle. Now, particularly the angles at D and H are 90 degrees. So right angle at each of these points. Now, looking at it from the perspective of the circles I just described, you see that this means that DR and HR are what? They are tangent. The center of that particular circle. So it's just at right angle with the radius. So this is radius, this is a tangent, and particularly they are equal. Okay, you can already deduce that. Okay, so this means that if you draw common tangent from R to the circle DAHE, then it's going to be tangent to that circle at exactly 2 points, which we already now know to be D and H. Okay, and the same actually applies to N. So N this time, the parts that will be, so here was DH. Now, if you take N, the parts that will correspond would be AE. So they will share AE. And it means that if you draw the line NE and NA, you're also going to tangent to the other circle. And this actually applies to, based on the symmetry involved, it applies to the circle BCGF as well. So RG and RC are tangents, and NB and NF also tangents. So you see that we kind of go with those pairings we identified earlier, which makes perfect sense. Like this is equal to this, equal to this. So this and indeed lies on what? On the radical axis of this circle. That's because the power of point n to both of these circles will be the radius of the circle at R at the center n. So let's call it Rn. So all these tangents have length Rn, and the power of the point n to both circles will now be Rn squared. So they are equal. So n lies on the radical axis. Same for R. So that line is the radical axis of the two circles, and vice versa. So based on the whole symmetry of what we're doing, this extends not just to these pairs of circles, but also any pair we pick. So how many pairs can we pick? So that depends on how we start. So if we know A is going to be part of these all 8 alphabets. So A is going to be somewhere. It doesn't matter where it is. So we'll assume A is in the first part, right? So once we have A, we just need to know what A is accompanied by. Then we'll have the rest of C, E, G. So if, for example, in this case, we had AE, so what will be left will be CG. And then once we have whatever we have here, we see that there are going to be exactly 2 circles passing through A and that point. They're going to be exactly 2 circles. And from those 2 circles, we are going to get 2 other pairings. And that will be all we need. So this means all that is required to determine our final result is to know what this will be. So this could be C, could be E, could be G. So we'll get 3. So altogether there will be 3. We have 3 of such scenarios where one pair is radical axis. Radical axis of one pair is the radial axis of the other, and vice versa. So that's as for that one. Now, how those points of Z, ZW, and A1. So how do they come in terms of those circles? How can we use this? So from what we have now, the fact that Rn is now the radical axis of the circle that has SK as radial axis means that they are going to be perpendicular, first of all. So we have right angle at Z. We have right angle at Z. And then now what we want to really do, let me erase some things here. So what we want to do is to identify that Z now will form some of the circles we had in mind. So particularly to form 4 circles. Okay, so we have Z here. Now, if you observe the angle SRZ being 90, so that actually means a lot. So if you look at this here, so you see that SR being 90, and we already had this to be 90. We had this to be 90. Pardon my diagram. So we have that Z is going to lie on this circle SD. So that's circle SDRH. So Z is going to lie on this circle. And not only this circle, so it depends on how you want to go about it. So you can take, if this is the circle now with diameter SR. That's one. Then also the another circle with diameter SN, another circle with diameter NK, and RK here. So we'll get 4 different circles. And for each of those circles, they correspond with some of these pairings we had here. So this one corresponds with DH. This one corresponds with passes through A and E, so AE. This here, NK, corresponds with PF. And this finally corresponds with CG. So based on what they correspond to, you see now that it's like a unique pairing between those circles and any pair of color of points with the same colors, right? And those were what we used to form our initial the circles for level 2. So this gives that we have. So this gives a pair for each of this circle. We have that they are only appearing once, and for each of these points, like Z, we already have 4 of those circles points. So for the other 3 points, we get 4 each, and then that completes the 12. So that means indeed we are looking at 3 points. So those 3 points from the circle. Now, so that's it for this, but just for the curious minded. So let me go all the way back to I had a complete diagram. So there's a lot more going on that we can for this. So we can just check it out. See, okay. Yeah. So let's see. Let me erase this. Okay. Okay, so going to do just a bit of, so now we have those two special points and then the other 3 points, the pink ones. Now what you might want to do is, if you consider these lines passing through three centers at once to be a circle, that adds the whole new picture to all this. So there are actually lots of circles involving those two special points U and V and the centers. Already there are some circles passing through the centers on these points. That's what created the points. But there are even more circles. There are even much more circles. Just give you a quick example. So we could try to just figure things out. So start with S and V, for instance. Um, okay, so let's start with S and V. Okay. So if you look at S, V, it passes through R already. Let's just try some other points. So yeah, so if you look at this, for instance, now just connected S, V, and some other center, L, and you see that it passes through yet another center, I. So in fact, just from S and V, there are still more circles we could get just from those two. I think they should probably still more. Show is not a bit. Okay, that doesn't work. Yeah, so you see that it passes through P and M. So you have like more and more of this that is coming in. The graphs, this one as well. Look at the last point we had there. Yeah, it passes through T. So just with S and V alone, you see that we already have let's say 3 more circles. I think probably more than that. Yeah, 3 more circles, and we already had 2 before, a green and a purple. So that's 5 circles. And for each of those circles, we are getting, it connects to 2 other centers, 2 different other centers. So if you look at the tree we included, that included 6 of the centers we had. So apart from S itself, there are remaining 5 more centers. One is associated with the green, another is associated with purple, so we have 3 more left. So in fact, we can actually draw one more circle. I think we had more than this. Yeah, I don't know why this went off. We had more than this. Yeah, so that goes through almost every other center. So if you observe from S, you can get to N as well through the purple. You can get to R as well through the green. So the only one that S doesn't connect to is kind of symmetric in a way is K. And the same will apply for K. K will connect to every other one as well. So yeah, so that's just one of these things. And then there are lots of straight lines involved as well, as I mentioned before. So this is just for S. And if you do that, you see that there are even much more circles passing through V. So yeah, so just stop this here now. So thanks once again for participation. This brings us to the end of our problem solving session for February. So can give the March one a go and then we'll look at that later. Thanks once again. Bye.